Betul. Hmm? Berapa? Jangan tu. Tak macam. Hmm. Tapi tak apalah, aku record. Hmm. Aku positif. Oh, dia lari je? Saya dah mula. Betul tu. Tak ada pula tu.
Okay, Assalamualaikum. Afternoon. You guys can hear me?
Yes, sir. We can hear you.
So, how's the preparation so far? Is it okay?
What?
What is how's your preparation for the final exams? You guys comfortable now?
Half.
Mhm.
It's about like
Just finish a
more like
tutorial.
30% profession.
Oh, okay,
So,
okay. 30% is good enough. So, we
so
still have.
sir, can you help us prepare even more?
Oh, for sure, for sure. Okay. Yesterday you have a review session with the Taliban, correct? Dr. Palan mention anything about the review class?
No, doctor.
Not yet, huh? Okay, and you can check with him. All right, so for today, how many people already inside here? 81, okay lah. So I think we can proceed now. Okay, as I promised to you, this is a review class before your final exam. Your final exam is going to be in 12th of February. Is that correct?
Yes,
Yeah.
sir. Yes, doctor.
In the morning, right? So 9 to 12, right? Okay, so as I promised also, I'm going to be reviewing last final exam question with you, so that you can understand. So you can basically, the most important thing is to understand what's the question required to answer, and then I will be reviewing only for the question that I met, okay. Then and then of course the rest of the question you can check with the respective lecturer, Dr. Palan, and also Dr. Iman. I think Dr. Iman already given you the review already. And then bear in mind, so everything that he teach you in
Sir.
this review session, so it's probably going to be,
This question is in the e-learning, right?
no, I haven't put any. I don't know. You can get it. This one is just this question is basically last year question. I think it's available from your. I don't know, maybe your senior or what. I haven't put anything from the e-learning. If you like, I can put it now. No problem. Okay, let me put that one first. Have you guys see your coursework, Mark? How do you find it?
Yes, doctor.
Everything satisfied? Everybody satisfied with the marks?
Yes.
Good.
But we want to see the lab test,
What?
the mini project, doctor, and lab.
Mini project report, huh?
Yeah.
So I'm not sure whether that they might finish the marking or not yet. They want only thing that is not included in the mark, right? 10%.
Yeah, not included. Yeah.
Okay, I'm trying to put the question to the e-learning so that you can download it from there. Okay, I put there already. Okay. Just to let you know that this session is only 1 hour because at 4 o'clock I have another meeting to attend to. So if you have questions, please ask quickly. Okay, let's go then to the question number 4 of the last year final exam. This question, if you can read, and then try to understand what the question wants. And then basically it's easy for us to start to answer. You are tasked with designing an electronic instrument. So did I share? No, did I share? Okay, I should bring. You are tasked to design an electronic instrument to measure soil moisture level using a soil moisture sensor. That sensor produce analog output, okay, in range from 0.15 volt to 4.5 volt. So notice from here, you already know that it's not starting from 0, right? So it's starting from 0.15 to 4.5. Okay, the system uses a 12-bit ADC. So you know what it is? 12-bit ADC to digitize the signal, and also you include a signal conditioning stage with an operational amplifier op amp to fully utilize the ADC range of 0 to 5 volt. So this is your task. Okay. The first one is just a description of your task, but not a question to answer yet. So just a task. So you're going to design instrument, electronic instrument, which is to measure your physical parameter is soil moisture, the moisture level. Okay, and then of course you're going to use a moisture sensor. But particularly the moisture sensor is only output the voltage of 0.5 to 4.5 volt only. So that's the range of the output of your sensor. Understand? So you have to picture in your mind. So that sensor, when you turn on and then want to measure the moisture sensor, the voltage output, the analog voltage output come out from the sensor is basically 0.15 to 4.5. Okay, and then the whole system use the 12-bit ADC. So you know that analog coming out of the sensor going into the ADC. That ADC is 12-bit. Okay, all right. Okay, and that reference voltage of this ADC is basically 5 volt, even though it's not mentioned, right? But it says the ADC range is 0 to 5 volt, meaning that the voltage reference is basically 5 volt. So that is the full range of the ADC measurements from 0 to 5 volt. Okay. All right. So this is your task. And then you need to answer the question A, B, C, D in order to finish your task. Okay, follow so far. Any problem interpret the question so far? All right, so let's look at the first question. The first question, A. The following tasks resolve the system design specification. Okay, and we have to answer part 1 and part 2 lah. So you have to do this part 1 and part 2 to actually answer the question A. So see the first part. Calculate the resolution of the 12-bit ADC in volt per step. This is a very bonus question that you can answer straight away. Probably the terms come differently, but this time the question asked in this question basically asked for the resolution of the 12-bit and in volt per step. So volt per step. So probably some other terms that can be used in in asking this kind of question, probably like what? Step, okay, or voltage per step, resolution. Those are the thing lah. All right. So I forgot one term. So I always choose to ask this question. What? Let me tell you when I remember. Okay. Anyway, this is one is just volt per step. So you need to calculate the resolution, but you have to answer in terms of volt per step, right? Okay. You know that the what we call the voltage reference for this ADC. So can you recall? Let us solve the first question first, no? Okay, let me share your screen, my screen here. Okay. So the first question is just asked about the resolution of the ADC. Okay. So we know that this is the first part. The ADC is 12-bit resolution, right? And then the voltage reference is basically 5 volt, right? So meaning that it measures from 0 volt to 5 volt. So that's what we know. Okay. So the resolution is just the range, okay, the ADC range divided by the 2 to the power of n, where this n is basically the bit, how many bits resolution of that ADC, right? So remember in the final exam question, I always put a cheat sheet or formula sheet at the back of the question. So in case you don't remember the formula. So, but sometimes I put, sometimes I don't put for easy formula, I don't put. But it's good for you to go and check out the cheat sheet, the formula sheet. If you stop, right? Okay, if you start, you can go back to very end of the page of your exam question. So you can find a lot of formula over there. You can find something that probably will help you answer this type of question, which is the one that uses a formula. Okay, don't forget about that. Don't always raise your hand. I mean, I might not be able to entertain all of you during the final exam. So you have to work by yourself. Like I said just now, is your start. Try to look at the cheat sheet if there is something that can help you out, right? Okay. And then what happened in the final exam? Normally, you guys tend to raise your hand and ask questions. But sometimes, if you ask a genuine question, I can entertain. But unfortunately, some of you actually want to discuss the answer. Is this one correct, sir? This way correct, sir? So that is not the way it is. So you have to answer. If you don't understand the question, so you can ask me to clarify the question. Okay, but you cannot ask me to discuss with you whether this one is correct or not correct. Okay, right? So that is not right in the final exam. So some of you probably ask for the answer some more. So that's too bad, right? So you have to work by yourself in the final exam. So you have to study and then prepare yourself before the final exam. In the final exam, you can answer the question easily. Okay, so this is a very straightforward question, which is the ADC range. We know that 5 volt. and then the n is a 12 bit, so the 2 to the power of n is a 2 to the 12. So you can find this one is equal to 5 over 4096, right? 4096. And then the answer is basically you can put it in voltage or you can put in millivolt. So I always write in millivolt, easy lah. I don't want to write in too many zeros inside there. Okay, so this is the answer. This bonus question, how much is the mark for this one? Is 2 mark. Okay, fair enough lah. Very easy, right? 2 marks. Okay. Right. Easy, lah.
Easy, doctor.
Easy, busy, right? So, but the ADC might not be coming in the same pattern like this, 12 bits, 5 volt, right? So, what is possibility that ADC comes in? Can it be 10 bit?
Yes.
No, cannot, doctor.
Cannot. It's
I
possible.
mean, 13 bits cannot.
It's possible that the ADC you can search the ADC parameter, ADC specification inside the internet, and it can be even 9 bit, 8 bit, 10 bit, 11 bit, 12 bit, 15 bit. So it depends. So that is the variation. Okay. So you must know how to handle that. Okay. Understand? If you're not sure, you can check out the internet the specification of the ADC, what kind of bit resolution they have. Okay, so that's one thing. Okay, the second thing, what is other variation we can get from here? Can the ADC be 3.3 volt reference voltage? Can or not? Can or cannot? Speak out. I'm malah nak tengok message.
Can, doctor.
Yeah. So you have to think that way lah. So that's going to be the variation. Okay. Don't get you don't get stuck on that lah because of different bit resolution and voltage reference, and you are already cannot do anything and raise your hand, ask me. No, I never seen this bit resolution for the ADC. That cannot be lah. So you have to think by yourself on that lah. Okay, so that's the first part. So let's check out on the second part. What is second part then? Let me go back to the question. The second part is derive and draw the op-amp circuit to scale and shift the input signal to the ADC full range. Okay, this one is very common. We teach you already how to do this one. We have to add on the signal conditioning. In this case, is amplifier lah, right? Okay, op-amp circuit that you can scale up, meaning you gain and then you can shift the input signal to some voltage level. Understand what I mean? You cannot miss this one. So this is 4 mark. So 4 mark, right? 4 mark. So 4 mark for this one. So we have to derive and draw. We have to draw, meaning that we have derived. We have to construct the circuit and then draw it. Okay, draw it. Derive, you have to calculate something, right? Value R1, Rin, R2, RF, and so on, right? So you have to put that derivation. And draw, so you have to draw the map, draw the circuit. So that's the thing. Okay. So this is a bit long, rather than just 1, 2 marks. This one is 4 mark, right? So we have to do some kind of calculation. Right. So let me go back to the okay. So part 2. We have to derive. So we need to understand. So we need to scale up and shift the sensor input signal to the level that we need. So we know that the sensor, the moisture sensor, output is from 0.1 0.15 volt to what? 4.5 volt. So the then the ADC full range is ADC full scale. Full scale is 0 volt to 5 volt, right? Okay. So these are the two things, the criteria that we need to consider before we can start. So since this one is not starting from 0, it's starting from 0.15. So the amplifier, the op-amp circuit that we should use is what you think?
Differential amplifier.
Say again, say loudly.
Differential amplifier.
Yes. So the amplifier type is differential amplifier. Okay. So because differential amplifier can shift the input signal to the level that we need, which is in this case 0.15, right? And then we can scale up according to the ADC full scale of 5 volt. Okay. So the differential amplifier is the one. So I think if you answer this one, you get mark already lah. Okay. So let's see. How do we derive the this amplifier? So I think by now you should know already what is the schematic should be for the differential amplifier pertaining to this kind of question. So I can close my eye. I can draw a very simple one of the amplifier. So do not forget, you need to be able to write this type of amplifier very easily. So if you don't know by now, cannot know what is the differential amplifier, you should practice. You go back and practice. Okay, right? And then this is one is what terminal. This is what terminal. This is non. This is non-inverting. This is inverting. This is non-inverting, right? Okay. So with that, we're gonna have a feedback resistor that connect to here. Okay. Then also we have the same value of resistor connected to the ground, and then here we have R input. Okay, and then here also we have R input. Right.
Sorry, Sezahari.
Yeah.
Screen delay lah.
I cannot really hear you. Can you speak up a bit?
Screen delay.
You cannot see my screen.
Screen stuck.
Oh, ya kah?
Oh. Yes sir.
Now okay lah. There?
Boleh nampak.
okay, sorry. Okay. Just slow, huh? Okay, now you see it.
Boleh sir.
Oh, but see, very slow. I don't know why. Never mind. I just continue and finish it. Okay, we have the sensor that's supposed to come in here. So in this case, our moisture sensor, right? And then over here, so that the one that we're going to shift the voltage to 0.5. So this V1, V1 must be equal to 0.15 volt. And then we have to design some kind of voltage divider circuit here, so that you can have the voltage at that V1 is equal to 0.15. So you have to determine this R1 and R2 value. Let me see whether you can see. Oh yeah, can see the image or not. No. What happened?
Tu lah sir. Start lagi lah.
Start lagi, yeah. So, I don't know. Let me. So now you can see, but when I change this, not moving. Even I'm making change here in my.
I can see R1, R2, RI, V out,
Okay, I know.
5 volt.
I know. Maybe if I share the whole screen, let me share the whole screen and see what happens.
I can see the mouse is moving.
Okay. Let me see. Entire screen and then the screen. Okay. So now you can see this one, right? If I move, that's better, right? Okay. So that's better. Okay, so let's proceed then. So you have V1 here must be 0.5, 0.15. So you have to design a divider circuit that produce V1 0.15 here. So I think everybody knows about this, right? So this is our feedback. So this equivalent R feedback, and this basically the one that goes to the ADC. Okay. All right. So this circuit, differential circuit, you must. This is V2. You must understand. You must you cannot have to think to draw this circuit, this kind of circuit. Can I say so or not? By now, I can ask you now, are you comfortable drawing a differential amplifier circuit schematic? Are you comfortable or not? Yeah, you must be comfortable. Otherwise, you're going to have a problem not to answer the final exam question. Okay, so RF and RI actually determine the gain. The gain ataupun what we call just now is to amplify. So we need to determine the gain for this amplifier circuit. What is the gain then? If you follow the formula, of the differential amplifier, the formula should be V out equal to differential voltage, which is V2 minus V1, and then time the gain, okay, which is RF over RI. All right? Okay, so you know that the V out, you want to mesh out of the ADC. So the V out supposed to be what?
Sure.
Why not? Okay. Oh my
Okay.
God. Okay. So V out, we know that we want to mesh the ADC one. So V out supposed to be 5 volt, right? 5. And then V2 is the V sensor, lah, right? V sensor. Okay. Which is the maximum of the V sensor is 4.5, right? And V1 is the low range, which is 0.15. Okay, and then this is a gain lah. So RF divided by RI. So by here, so you can resolve for the gain or RF RI. Which is equal to, if you calculate, it's basically 5 over 4.35, different 4.5 minus 0.15 is 4.35, and then 5 over 4.35. Then it's equal to 1.49, 149. Okay, that's the gain. Okay, once you get the gain, so you can find for the you can assume one of the resistor or RI or RF, and then you get the other one. So in my case, I'm trying to basically assume RF, assume RF equal to 1K, then you get R1 equal to around 870, right? 870. No, it's ohm. Okay. So now you resolve for RF and RI, because this one down here, the RF and RI also the same value. Okay. Right. So the only thing left is how to reset this voltage level at the V1 equal to 0.15. V1 is very easy also. You want V1 equal to 0.15. While you know the voltage is 5 volt here, 5 volt there, then you can still see my it's stuck again. Okay.
Assume
Right.
R1 equal to 3 or 870.
Yeah. You have to find the voltage from voltage divider lah. Okay. Like if you set one of the resistor equivalent to one, and then you can find one. For example, for my case here, I put R2 equal to 10K ohm. So V1 will be equal to 5 volt times 10 over 10 plus R1, right? So equivalent to 0.15, because the voltage V1 here, I want to equal to 1.5, so I'm running out of space already here. But if you solve for R1, so R1 will be equal to 3 ohm like that. So this is easy to get the value of R1 and R2, right? So this one you find, this one you find. So your circuit is basically done. right? And then you can you have all the values, and then you have the circuit, and then I think it should be okay. You answer the question already. Okay. Can you see all the things that are right here? Okay,
Yeah.
so the part 2 is done for 4 mark. You need to draw the circuit, and then you have to derive all the values for R1, R2, RF, RI. Okay, and that's it. You have 4 mark. Okay. Oh, we are running out of time already. We delayed. So it's only part 1, only part A. How do we? Okay, so we quickly go back to part B lah. So we cannot waste time. No more. Hopefully you can catch up. So part B is basically what? Part B is consider the sensor output. Ini lagi senang. Consider because you know already everything. So consider the sensor output signal is 2.75. So you need to determine the condition voltage, meaning that the voltage, the output from the signal conditioning that goes to the ADC. What is it? What is it? Right. Okay. So let me get the new page here. So part B, let me share again. Okay, so okay, for input 2.75 volt, right? Coming from the sensor, 2.5 volt, 2.75 volt. So we want to see the condition signal, the condition voltage out of the signal conditioning circuit. So V output lah, V out, V out for the condition one, we call it V condition. Okay, is equal to the V2 minus V1 times the gain, right? So V2 is actually the voltage that is you are working now, which is 2.75 minus 0.15, and then you need to time by the gain, which is 1.149. Yeah? Okay, so then the V condition is just to get, if you calculate, it's around 3 volt. Okay, as easy as that one.
Doctor, we can't see the screen.
Oh, you cannot see the screen. How come? Okay, yeah, that's it. Yeah. So VL or V condition is V2 minus 1 times the G, according to the differential amplifier formula. And you get this one. Okay. Right? So that is part B. So we need to rush out, go on to the next part so that we can finish this one. Part C, part C, propose. Okay. So this question, this kind of question is basically, it's up to you. So you can give some ideas. Huh? But for this one, the question as proposed as to the sampling rate if the temperature change at the maximum frequency of 2 Hz. So temperature change 2 Hz every 1/2 seconds. All right. So explain your reasoning and discuss what could happen if the sampling rate is insufficient. So this I explained in our lecture according to Nyquist theorem, sampling theorem, right? Theorem. So you must sample the signal is twice as an input signal lah. So for this case we have 2 hertz of the temperature change in 2 hertz, so we have to sample the thing twice of that, so maybe 4 hertz. But recommended is over sample lah. You can sample 10 hertz so that you can get the result better. Right? So that's the theorem lah. Okay, so you have to explain why, what's the reasoning lah. What is the reasoning? Why we need to do this sampling rate like that? Okay, if the sampling rate insufficient, so there will be what we call it as a aliasing that will happen. So you cannot reconstruct back the actual signal, signal that coming in. So you have to do twice of that input signal frequency for your sampling. Okay, if you put over sampling like 10 hertz, that will be even better. Right. Okay, so that is simply the answer for that one lah. I think kalau you read the lecture, this is from the lecture note, so you can answer this one. Okay, and then D, compare successive approximation register SAW and flash ADC architecture. This one is for ADC lah. Recommend the more suitable ADC type for this system and justify your choice. This is the same thing. This is from the lecture note also. So you have to compare between SAW type of ADC or flash type of ADC. Okay. So from the lecture note, you can see, you can compare in terms of speed, power consumption, cost, resolution, and then you can start do your recommendation. So I can put it here. You can see. You cannot see. So my answer for that, I have to share the screen again. Okay, so that the answers you can do the kind of table like this. This is all coming from the lecture note. So the speed is for SAW is moderate, flash very fast. Power consumption for SAW is low, for flash is high. And cost, SAW is cheap, flash is expensive. And then resolution basically moderate for the SAW and limited for the flash. So recommended high resolution to have it. So you need to use SAW for moderate speed and sufficient for low. So you use basically you can recommend SAW. So this is your justification. It's low power consumption and cost effective compared to the flash types of ADC. So this is the answer. But this one is theoretical. So the answer is like that only. Easy or not? Supposed to be very easy for you to answer.
Sir.
Ya.
Ada soalan yang kena lukis-lukis tak, sir?
Apa dia?
Ada soalan yang kena lukis-lukis design SAR ni di AC tu tak?
Tak clear lah, sebab soal dia tak clear. Muhammad apa ni? I cannot catch your question. Can you repeat that question again? Soalan macam mana?
Ada soalan yang kita kena lukis tak, sir?
Dia macam double lah, suara you buka dua mic ke macam mana? Can you write on the message lah? Senang saja, I boleh tengok.
Kami ambil.
Okay, anyway, tak apa. So I think when I get when I understand the question, then I try to answer. So I want to go directly to the question number 5.
Tak apalah.
Right? Question number 5. So also you have to read carefully and then try to understand before you can start answering it. Okay, electronic instrumentation is essential for solving measurement problem in various domains. Combining principle of measurement, science, and data acquisition, data processing, answer the following question. So the part A here, you have to discuss the key consideration when designing an electronic instrumentation system to measure physical quantity, include the role of transducers, signal conditioning, and data acquisition component in your explanation. So key consideration, this is the thing you have to, when you design a instrument, so what are the key consideration? Okay, what do you think the answer is? What is the first key consideration in designing a electronic instrumentation?
The transducer.
Yeah, transducer, right? So transducer, you find it must be suitable based on the variable environment that you are actually work with. You cannot just simply you take the transducer that is not suitable for the condition that you're going to work with. Okay, for example, if thermocouple is chosen for measuring temperature, so you have to choose. You know, there are a lot of transducer in measuring temperature, right? You can use LM35. Okay, you can use other sensor also. You can use thermocouple. But for the case of the high temperature, like oven, so the best transducer is basically like thermocouple, because it can withstand the high temperature, and then it can provide voltage output proportional to the temperature. So it's accurate, more accurate. Okay, that's one thing. And then second key,
Conditioning circuit.
yeah, you need to consider your signal conditioning circuit, right? So whenever you use, for example, if you take, for example, just now, we are working with thermocouple, so you definitely have to get a very good signal conditioning circuit. You know that the response from the thermocouple is very small, so you need to do, amplification, high amplification of the output from the transducer thermocouple. Okay. So some case, if the errors, is error, high error, so a lot of errors from the environment, from systematic kind of things. So you have to use error correction method. For example, you have to have filter circuit. If you have a noise, a lot of noise, you can use a filter circuit to filter out all the noise. Okay. And then the third one is what? Once you have filtered the signal, you have the transducer, you choose a correct transducer, and then you have a signal conditioning to work with the transducer, and then get the value output of the sensor correctly now in a very good level. So what do you do next?
ADC.
Yeah, this is ADC, or overall is the data acquisition. So ADC, you have to check the accuracy or the resolution of the ADC, that you can get a very high or accurate value when you read data from that sensor or from the signal conditioning circuit, because it coming from the signal conditioning circuit, right? So those are the things that the three key that is you have to consider in designing the electronic instrument. Okay, so I have the answer sheet for that one here. Maybe I think after this I share with you all this answer. Okay. All right. And then B, the common three type of errors that can occur in electronic instrumentation system: systematic, random and human errors. Suggest strategies to minimize this error during system design and operation. Okay, so this is also come from the, I think your lecture note also, but probably you need to understand a bit lah. Okay, kalau systematic errors maksudnya macam mana? It's consistently error, right? For example, our method last time is to do averaging, right? So those are the things that we can, you can handle for the systematic error. Let me share you this answer so that you can see. Okay. So if a systematic error, basically measurement is always drift over time or have a constant error over time. So therefore you have to do to sustain the accuracy. You do a periodic calibration. You have to calibrate it. Yeah? Or probably the other method you can use averaging. You know, you can get the error back to the accurate one. Okay, if the random error you cannot determine lah. So sometimes it's some error, sometimes it's not error, sometimes it's good, sometimes it's bad, right? Because of the environment. Therefore, you need to do a proper shielding or filtering so that you can mitigate the error. So that's the best you can do for random error, because this is undeterministic. So sometimes it's good, sometimes it's bad. So you have to find the root cause of the influence of the sensor of the errors, and then you do some mitigation, like do a proper shielding, filtering, and so on. And last one is a human error. If human error, if your measurement is actually display reading, right, then the display is not proper, so human will record it incorrectly, right? So the best is you do the automation, so you don't have to do reading, or you have to directly record to the file, or you have to make a system that is easy to read display, so that you can minimize the risk of human error. Okay, first you can directly capture the data into a file so that there is no human error. You bypass the human. Or if you cannot do that, you have to design such an easy to read display so that human can really easy reading it and then make it a proper recording and correct. Okay, so those are the answer for that question. So it's almost 4 already, so let me share back to the question. Okay, so this question is very quick one, because I just need to ask about the thing so that you can understand. But this is a good example for checking your understanding of this, what we call data acquisition system. A company requires temperature monitoring system for industrial furnace operating between 800 degrees Celsius and 1,200 degrees Celsius. This is very high Celsius, high temperature. You are requested to design a system using thermocouple. The thermocouple is the only thing that's the only transducer that's suitable for this condition. Signal conditioning, you have to have a signal conditioning with 100 gain, the gain of 100, and your ADC is 12 bit, and your voltage reference is 5 volt. This almost the same like the question number 4 just now, but if you understand that one, so this one should be easy. The additional information said here is a thermocouple has sensitivity of 40 microvolt, right? A complete the following tasks so that you can actually answer all these questions. So first, you need to calculate the resolution of the system in terms of temperature. Can you not gonna calculate in terms of temperature? So you know you are working on all of this. So let me go back to the. I think I can spend more time on this. Hopefully you can see this. This question number what, Andri?
C.
Yeah, see. Okay, see, we have a temperature, a furnace is 8 degree until 1200 degree. Yeah. So this, the range is 400 and basically 400 degree C. And then it says that you are having a signal conditioning. See, this one is not starting from 0 again. So this one is basically, it's going to use a differential amplifier.
Doctor, I'm sorry to interrupt, but we didn't see.
Oh, you still cannot see. Huh? How come? Huh?
Yeah.
Too bad. Huh? Yeah. Okay. I cannot see my question then. All right. So let me see. And then we work with this amplifier. Oh, I cannot see. Okay, it's slow. And the gain is equal to 100, right? Okay. Gain is equal to 100. And then the ADC. ADC is what? Resolution just now 12 volt. It's 12 volt, 12 bit. And then 5 volt reference. Correct? Have to go back and forth to check this thing. Yeah, 5 volt. And then and some other information is 40 microvolt per degree Celsius. That one is the sensitivity of thermocouple sensitivity. Right. So you are using a differential amplifier, and then you get this all information. Then you need to calculate resolution in terms of temperature, not voltage. How do you do that? Resolution in terms of temperature instead of normally you can calculate easily in terms of what we call voltage kan, tapi ini dia tanya untuk degree Celsius. Macam mana? Okay, so in order to calculate this, you have to know that this is the sensitivity, right? And then this is the gain. So every voltage that come out from the sensor, the TC, the TC output, will be multiplied by 100, right? Because the gain is 100. So every single, like this one is 40 degree per degree Celsius, 40 microvolt per degree Celsius, right? So this 40 microvolt per degree Celsius must also time 100 lah, so that you can get the actual voltage, voltage per degree Celsius after the amplifier, right? So what do you get for this one?
Stop, brother.
4 millivolt.
4 millivolt, right?
Yes.
4 millivolt per degree Celsius, right? But you need to answer the resolution in terms of what we call degree Celsius. Not this one is in volt. So you need to know also the resolution of your ADC, which is ADC resolution. Basically 5 volt divided by 2 to the power of n, which is 5 volt divided by 4096, which is equal to 1.22 millivolt. Right. Okay. So that is the resolution of the ADC lah. Right. So when you have that one, because you are measuring at the after signal conditioning, right? So you want to get the resolution per degree Celsius. In degree Celsius, basically you need to get this resolution.
Tak lawa.
Lupa juga. And let me finish this one first, and then I will show you. 1.22 millivolt divided by by 4 millivolt per degree C. Then you get cannot appear here. Why? Don't appear here. Reshare will appear. Okay. So what do you get? Here you can cancel out this one, 1.22 millivolt divided by 4 millivolt. You can cancel that one. This degree C will go up, right? So what do you get? 1.22 by divided by 4. What do you get?
0.305.
0.305, right? Then this is in degree Celsius. Set the resolution of the cannot see him. Okay, is the resolution in terms of degree Celsius. Okay, so that question number. C1, C1. Okay, that's the only thing that you have to calculate, right? So the second one, the two challenges encountered during the implementation of the system: high temperature noise and thermocouple durability when long exposure to heat. Suggest a solution to this problem. Okay, and then now that's the last one. Okay, so I have the solution written in here. I can show you. But the calculation of that is just like that. So to get the resolution in terms of degree Celsius. So let me share this screen. Last one. So that is the solution. High temperature noise. This could be due to electromagnetic interference from the furnace environment that can distort the reading. Cable shielding is and grounding, the proper grounding is the one that can solve for the noise, right? High temperature noise problem, okay, which is expected to be due to the electromagnetic interference from the furnace environment. So that you can handle that one by using cable shielding and grounding. Okay. Second one, thermocouple durability, long exposure. Of course, it's very hot inside the furnace, right? So long exposure to heat, it will degrade the thermocouple. So you need to select type of thermocouple so that from the high temperature resistant material, such as platinum, radium alloy, and so on, so that it can prolong its lifespan. Okay, so that's a basically simple answer for that. The last one. So I think that's it. Enough lah. Cukup. For all of the two questions. So my question inside the final exam also two questions. So you can expect a kind of question pattern. Okay. Then of course it's not going to be the same. Definitely, like a variation that I mentioned to you, have to consider. So those are the things that you have to prepare before the final exam. Then do not think about other things, but some of the what we call a theory part. So you have to read a bit all the all the, from the lecture note, you have to read through and then catch something to prepare if there is any theory question. But for the calculation wise, so they're going to be quite the same pattern, but different environment, different situation probably. Okay. So I guess that's it for our preparation for final exam. So I don't want you to study too much for the thing, but focus on the thing that I give to you from the lecture and also for this preparation. And that's it. You can actually can answer the question basically. So there's somebody raise your hand. No, please ask question. What is your question? I give you another 3 minutes also. I need to go now. Somebody raise hand just now. Apa? You like to ask question? Or any from the floor, if you have any question, any tips to ask, so this is the time. So this is the last time we meet for this course. And then after that, you're going to be sitting for your final exam. Yeah, Alani Moyat student. Alani Moyat.
Doctor, for the exercise, we had a question asking for the design for the ADC approximation successive and for the ADC flash. So this design question will not come up in the exam?
For the ADC, right?
Yeah, designing.
Designing, no.
So the successive approximation and flash ADC will come as a
But
theory
I
part
think
of.
in theory, so you have to read it a bit. You have to understand how it is. Like just now, the theory question about asking of flash and also SAW, right? So that's a kind of theory.
Okay. So only a theory.
Okay.
Okay, thank you, Doctor.
All right. Okay.
Doctor?
Yeah.
Can we get the answer scheme for the question 4 and 5?
Okay. When I come back from I will try to put up the answer sheet.
All right. Thank you.
Simple answer. All right. Okay. I cannot wait. I cannot call anymore. So I need to go. So if you have no more question, we can end our session here today. All right. Thank you very much for those who come into class. And then this one will be recorded. It will be posted inside the e-learning, so you can check it out from the e-learning. Yeah, Alani.
Doctor, one last question for the DAS, for the data acquisition system.
Okay.
Also, it has a design question, so also will not come up.
No, theory only. So you can read now by theory.
And signal conditioning lux, Doctor.
Yeah, signal conditioning you have to understand. Like I teach you how many times already, so you have to understand clearly.
No, I mean if the question like give me a range using the lux, same as the tutorial part.
Using what?
Lux. The
light intensity.
Yeah, the light intensity.
I cannot answer you because the parameters, the physical parameter to measure can be anything. Can be voltage, can be lux, can be resistance, can be moisture, and so on. Any transducer can measure. So those will be as is general.
Okay, Doctor. Thank you.
Okay. All right. So thank you, everybody. So good luck for your final exam. Hopefully you do the best. All right. Thank you very much. Bye bye. Assalamualaikum.
Thank you, Doctor.
Waalaikumsalam. Thank you,
You're welcome.
Thank you so much.
Thank you, Doctor.
Thank you, Doctor. Thank you, Doctor.